Hello, and welcome to my presentation for the ISC 2020 Research Poster Session. My name is Mike Zielewski. Today, I will present my work, Challenges in Solving Scheduling Problems with the D-Wave Quantum Annealer. First, I will introduce quantum annealing. Quantum annealing is a meta-heuristic that minimizes the quadratic unconstrained binary optimization problem, or QUBO. Two important things to note about the QUBO are the variables are binary and terms have a maximum degree of 2. By exploiting quantum mechanical properties such as superposition and tunneling, quantum annealing offers speedups over classical solvers. Next is the motivation for this work. Quantum annealing requires that problems go through the preparatory steps of formulation and embedding. These steps introduce overhead and influence performance. The objectives of this work are to determine how significant the overhead is and how performance is affected. In this work, we select the NP-hard Job Shop Scheduling Problem, or JSP, to evaluate quantum annealing. In the standard JSP, we seek an arrangement of a set of jobs on a set of machines. We use a JSP formulation for quantum annealing that was introduced in another work. First, a time boundary T is defined. Then, at each time within that boundary, variables are created to indicate the starting of an operation. We use two tools for QUBO generation, D-Wave binary CSP and PyQUBO. While both tools use the same amount of base variables, we observe that D-Wave binary CSP introduces auxiliary variables for larger JSP instances. We consider using D-Wave binary CSP to be analogous to using a less efficient formulation. After problem formulation is embedding, in which we seek a mapping of QUBO variables to physical qubits. Qubits in the D-Wave quantum annealer have limited connectivity and are arranged in a grid of unit cells, shown in the rightmost figure. Qubit connectivity can be increased by chaining multiple physical qubits into one logical qubit. In the leftmost figure, we show a system of 3 fully connected variables which cannot be directly embedded into the unit cell. By representing variable x as a chain of 2 qubits, as shown in the middle figure, the system can now be embedded. To find embeddings, we use the heuristic tool minor-minor. Results from the annealer must undergo unembedding to determine the value of each variable. When all qubit values representing a variable match, the variable takes on that value. When qubit values do not match, the variable chain is broken and chain break resolution must be performed. For this, we compare two methods. The first is majority vote, in which the most frequently occurring value is selected. And the second is minimize energy, in which the value minimizing the objective function value is selected. Now, I will present the results of this work. First, I will discuss embedding. In the figure on the left, we see that as the number of variables in a QUBO increases, so does the embedding time, resulting in a large overhead. In the figure on the right, we see that the embedding algorithm often fails for large QUBOs, which is represented by the green area. Because D-Wave binary CSP requires more variables than PyQUBO, its embeddings are larger and it fails more often, up to 83% of the time. Next are some results from the annealer. This figure shows a negative correlation between the amount of valid schedules found and embedding size. This indicates that there is a cost-performance trade-off in embedding, in that spending additional time embedding may result in a better performing, smaller embedding. Lastly, in this figure, we compare the chain break resolution methods for QUBOs of increasing complexity. These results show that minimized energy consistently outperforms a majority vote. We conclude this work with the following takeaways. Inefficient formulation methods or tools degrade performance. Embedding is costly, but repeating it may yield better performing embeddings. Minimized energy resolves broken chains better than majority vote. One promising area for future work is creating embedding methods that are faster, use fewer qubits, or result in higher performance. Thank you for your attention. If you would like to contact me or my colleagues about this work, please use the email address on this slide.